Hi, here we are at geometry again. Today we're going to talk about circles, tangent lines. A tangent line is a line in the plane of the circle that intersects the circle in exactly one point. And the point that it intersects at is called the point of tangency. Our objective for this unit, for this lesson, is to use properties of a tangent to a circle. So, a tangent to a circle is a line in the plane of the circle that intersects the circle in exactly one point. So, line AB is a tangent line. The point where a circle and a tangent intersect is called the point of tangency. So, point B is the point of tangency. Ray BA is a tangent ray, and segment BA is a tangent segment. It's essential that you understand a radius of a circle and the tangent that intersects the endpoint of the radius on the circle have a special relationship. That's where we come into Theorem 12.1. If a line is a tangent to a circle, then the line is perpendicular to the radius at the point of tangency. So line AB is tangent to circle O at point P. Therefore, you know that this forms a right angle. This is perpendicular. Line AB and the radius OP are perpendicular. So we can use this information to find values. What is the value of x? Let's look at example A. In example A, we know that if line LM and line NM are tangents to this circle, circle O, then LM forms a 90-degree angle, and NM forms a 90-degree angle with these radius. And therefore, this shape, LMNO, which is a quadrilateral, all quadrilaterals have a total of 360 degrees. So we can find the value of the variable by saying 90 plus 90 plus 117 plus x is equal to 360. So we can subtract 90, 90, and 117, which is 297, from 360. When we subtract 297 from 360, we're going to get that the value of x is equal to 63. So the measure of this angle, the measure of angle M, is equal to 63 degrees. So because we knew that these tangent lines form right angles with the radius, we know that in this quadrilateral, all angles add up to 360. So we know 90, 90, 117 plus the angle x are equal to 360. So let's look at example B. What kind of a shape is that? That one's a triangle. So we can use that we know if DE is a tangent to circle O and OD is a radius, that forms a right angle. We know that all triangles equal 180 degrees. Therefore, 90 plus 38 plus x equals 180. So when I combine my terms, 90 and 38, I'm going to get 128 plus x is equal to 180. Therefore, x is going to equal 52 degrees. So tangent lines, segments, rays, whatever, they form right angles with radius of circles. Theorem 12.2. If a line in the plane of a circle is perpendicular to a radius at its end point on the circle, then the line is a tangent. So if it forms a right angle, then you can prove it is a tangent. So this is kind of the converse of the original theorem. So let's use this. We want to find a radius. What is the radius of circle C? Well, if this triangle ABC is a right angle, how can we find the value of x? I know the long leg here is 12. I know the hypotenuse is x and 8, and I know the short leg is x. So I can use the Pythagorean theorem. X squared plus 12 squared is equal to, this is the hypotenuse squared, so x plus 8 squared. So you'll remember from your work with quadratics, I have x squared plus 12 squared is 144 is equal to, x plus 8 squared really means x plus 8 times x plus 8. So I have to multiply these two binomials. Some of you may remember using FOIL to do this. So I'm going to get x squared plus 8x plus 8x, so 16x. 8 times 8 is 64 when you FOIL it, right? So I have a quadratic on the right side of my equation. In order to solve this equation, I want to collect everything on one side or on the other. So what I can do is I can subtract x squared from both sides. So my x squareds are gone. And now I want to subtract 64. 144 minus 64 is going to leave me with 80. So 80 is equal to 16x. In order to solve for the value of the variable, I want to do the opposite of times 16, so I want to divide by 16. So 16 goes into 80 5 times. So x is equal to 5. So this is 5, and this would be 5 plus 8 for 13. All right, so you try example B. See if you get it. Remember, when you do x plus 6 squared, it means x plus 6 times x plus 6. So like what I did here, we want to FOIL it. So don't lose that middle term. It means that you're going to have 6x in the middle twice. So try that out, pause the video, and then push play when you're ready to check your work. This should be what your original equation looks like. X squared plus 10 squared is equal to x plus 6 squared. When you simplify on both sides, this is what it should look like. Then you want to subtract x squared from both sides, and therefore they both just cancel out. Going to subtract 36 here. 100 minus 36 is going to give us 64 is equal to 12x. And I want to use the division property of equality here to find that the value of x in this case is going to be, when I divide 64 by 12, I'm going to get a decimal. It's going to be x is approximately 5.3, because it's going to be 5.3333 repeating. So 5 1/3, if you'd like. All right. We can also identify a tangent by determining whether or not this is a right angle. Is this a right angle? Well, how would I find out? I would use the Pythagorean theorem. If it works, this is a right angle, and therefore ML is a tangent to circle N at point L. If it's not, then it won't come out when I use the Pythagorean theorem, remembering that that's the hypotenuse. So, is 7 squared plus 24 squared equal to 25 squared? If it is, then ML is a tangent to circle N. So 7 squared plus 24 squared is going to get us 625. And 25 squared is 625. So because this works, then this is a right angle. So yes, ML is a tangent to circle N at L, because the point of tangency is also the vertex of the right angle. It forms a right angle. So because it forms a right angle, then I know that NL is a radius, it's perpendicular to the tangent, therefore this is a tangent, because that's a rule of all tangent lines. Theorem 12.3, if two tangent segments to a circle share a common endpoint outside the circle, then the two segments are congruent. So if BA and BC are tangent to circle O and they share B, that means that these are congruent to each other. In the figure at the right, the sides of the triangle are tangent to the circle. The circle is inscribed in the triangle. The triangle is circumscribed around the circle, about the circle. Therefore, remember the theorem we just had, these tangents share a common endpoint, so they're congruent to each other. These tangents share a common endpoint, so they're congruent to each other. These tangents share a common endpoint, so they're congruent to each other. So, circle O is inscribed in triangle ABC. What is the perimeter of triangle ABC? Well, AD and AF are tangents, and they have a common endpoint at A. So, if AD is 10, then AF is 10. BD and BE share a common endpoint at B. So therefore, if BD is 15, BE is 15. And then lastly, CF and CE have a common endpoint. So if CF is 8, CE is 8. So the perimeter is when you add up all of the sides. 10 and 10 is 20. 15 and 15 is 30. 8 and 8 is 16. 20 plus 30 plus 16 will give us our perimeter of triangle ABC. 66 centimeters is our perimeter. Take a look at example B. See if you can figure this one out. Circle O is inscribed in triangle PQR. Triangle PQR has a perimeter of 88 centimeters. What is the length of this segment right here, QY? Again, RZ and RY share a common endpoint, so if this is 17, this is 17. PX and PZ share a common endpoint, so if PX is 15, then PZ is 15. I don't know what these two are, but I know they're congruent to each other. So I know that 15 and 15 is 30, 17 and 17 is 34, and then I have two x's equals the perimeter of 88. So 30 and 34 is 64. So when I subtract 64 from 88, 2x is equal to 24. So x is equal to 12. So this is 12 and this is 12. When I add them all together, 12 plus 12 plus 15 plus 15 plus 17 plus 17, I get the perimeter of 88 centimeters. That's the end of our notes. We'll work on this tomorrow more in class.